Time to finish up our examples from section 3.5. So we are on example 4 right now, and the function that we're looking at is y equals 1 plus the secant of x times sine of x. And remember, we want to find the derivative dy dx for this function. And you can see here that even if you did distribution on this, because that is a thing that you could do, you'd have sine x plus secant x times sine x. If you think that looks nicer, you can work with that. But in either case, you're going to have to use a product rule. So we would either take the product of these two terms here overall, or you'd have to take the product of those two functions there, secant x times sine x. So yeah, either way is an option, and you should end up with the same answer either way you do it. I'm going to go with the factored form as the function was originally written, but if you want to try the other one, you can. So yeah, product rule time. Okay, identifying that there is a product overall there. And so I'm going to take my first function, 1 plus secant x, times the derivative of the second function, sine x, and then plus the second function, sine x, times the derivative of the first function, 1 plus secant x. And there we go. Okay, take those derivatives. Got our 1 plus secant x. The derivative of sine is cosine. So put that in right there. And then sine x here. And the derivative of 1 plus secant x, well, the derivative of 1 is going to be 0, so that doesn't have an impact here. But the derivative of secant x is secant x tangent x. Okay, you knew that, right? Right, because you're memorizing these. All right, just got to keep emphasizing that for you guys. Okay, these aren't going anywhere. Especially if you go on to Calc 2, there's a lot of trig in Calc 2, so you will want to know these. Okay. So let's try and simplify some things here. To help us do that, one thing I'm noticing is the secant. Secant is 1 over cosine. So how about if we wrote it like that and then distributed this cosine x from the outside there? That's going to cause some good cancellation for us. And let's do kind of the same thing over here with our second term. See if the secant and tangent, if anything nice will happen there. We'll have 1 over cosine x times sine x over cosine x. All right. And yeah, let's multiply. So distribute your cosine x here. I'm going to have cosine x plus 1, since those would cancel, secant times cosine. And then over here, we'll have, well, these are all just fractions. Sine over 1 times 1 over cosine times sine over cosine. Ultimately, that would give us sine squared x over cosine squared x. Okay. Which is the same thing as, I'll put it down here, cosine x plus 1 plus tangent squared x. Okay. But remember back from trig, tangent squared and 1 actually come together into a Pythagorean identity as well. This one's not quite as common as your sine squared plus cosine squared, but it's still Pythagorean. Okay, so Pythagorean identity. And if you ever need to rederive these, because on occasion, we don't always remember the best. And so remember, if you just know sine squared plus cosine squared equals 1, that's going to get you a long ways here. Because remember that tangent is sine squared divided by cosine squared. So if you divide every single term in your original Pythagorean identity by cosine squared, you're going to come up with this new Pythagorean identity involving tangent. Tangent squared x plus 1 equals secant squared x. And that's exactly what we want to use right here, because we have 1 plus tangent squared. 1 plus tangent squared plus 1. That is all just going to be secant squared x. So let's do that. We got cosine x plus secant squared x. There might be further simplifications you can do, but that looks pretty darn good to me for our derivative. All right, so there's number 4. And now for our last example, number 5, we are going to find the fourth derivative of y equals 9 cosine x. Okay, oops, got a little ahead of myself there. I just wanted to write the original function down for us. Okay, so original function, y equals 9 cosine x. Let's start taking derivatives. Okay, our first derivative, y prime, would be 9 times the derivative of cosine x, which would be 9 times negative sine x. Okay, so negative 9 sine x for the first derivative. Okay, do it again. Second derivative, same idea, negative 9 times the derivative of sine x. Okay, that'd be negative 9 times cosine x. That's our second derivative. And do it again. Negative 9 times the derivative of cosine x. Very exciting. That derivative is negative sine x, and so we come up with positive 9 sine x. And for the fourth derivative, do this one more time. Remember that notation usually switches here. A little parentheses 4 up in the superscript indicates your fourth derivative. And so we're going to have 9 times the derivative of sine x, and that is 9 cosine x. Okay, so that is the fourth derivative of our function. Now notice here, the fourth derivative of our function actually goes back to equaling the original function itself. The fourth derivative of y equals the same function as original y. They both equal 9 cosine x. And you'll notice that this will happen from time to time because of the cyclical nature of the sine and cosine derivatives, how they are derivatives of each other, but just changed with a negative sign. So yeah, this is a cyclical process here. And if you needed to find some really high derivative of a trig function like this, a fairly simple sine or cosine type of deal, you could actually break down that cyclical pattern to help you find, say, the 52nd derivative of this function, because it's just going to keep repeating and cycling through these 4 things over and over again. 9 cosine x, negative 9 sine x, negative 9 cosine x, 9 sine x, and then you're back to where you started. So that's kind of a nice thing to know about the sine and cosine derivatives. Even if you don't end up using it too often, it's a nice property because of the nature of that sine and cosine derivative there.